Hi everybody, in this video we're going to talk about quadratic functions. With linear functions, the key feature of a linear function is that you consistently add an amount, and with exponential functions you consistently multiply by a certain amount. And with quadratic functions, you don't consistently add or multiply by a certain amount. The key feature for a quadratic function is that the input is going to be multiplied by itself at some point. In this case, it's showing up in the equation here where you have x squared because the input is x and it's being multiplied by itself twice. And specifically with quadratic functions, it's always multiplied by itself twice. There are other functions like cubic functions where they're multiplied by itself 3 times. But with quadratics, it's just multiplied by itself twice. And you can also have other parts to the equation, like in this case, the x is multiplied by 4, which is kind of more of a linear relationship that shows repeated addition. But because you also have this x squared in the equation, that makes the overall function a quadratic function. And whenever you graph quadratic functions, the shape of the graph will always be this parabola shape. And one of the interesting things about parabolas is that they're related to cones. Because if you take a cross section of a cone that's parallel to one of its sides, so you can see this two-dimensional slice through the cone that's parallel to the side of the cone, the shape that creates on the boundary of the cross section is a parabola. And so every parabola corresponds to some cone. So this graph of a parabola that I have on the left, it probably corresponds to a cone that's a little bit taller and skinnier than the cone that I have drawn here. But every single parabola will correspond to some cone, which is kind of an interesting. Another example of a quadratic function would be this number sequence that my dad sent to our family's group chat. And this is the number sequence I used at the beginning of the semester to help you guys understand how to write proofs. But if you look at the equations that me and my sister came up with to represent this number sequence, notice that both of them have the variable multiplied by itself. So in my function rule, I did 2 times the term number squared minus 1. And if you simplify that, so there's no parentheses, that gives you 4x squared minus 1, because 2 squared is 4 and x squared is x squared. And then with my sisters, she wrote it as the multiplication of 2 odd numbers. But if you FOIL this out, or if you multiply 2x times 2x, that still gives you the 4x squared. So even though it's written in factored form, you still have the input multiplied by itself at some point. And so that's what makes this a quadratic function. And you can see that if you graph the terms of the function. So in this case, the x value represents the term number, and the y value represents the value of the term. So the sequence 3, 15, 35, 63, 99, etc. can be graphed on the coordinate plane in this way, where the first term is represented by this point at 1, 3. The second term is at 215. The third term is at 335. The fourth term at 463 and 599, etc. And what's kind of interesting is if you were to follow this pattern backwards, it would still create this parabola shape. So maybe the easiest way to follow this pattern backwards would be to use my sister's pattern, because hers was to do like 1 times 3 and 3 times 5 and 5 times 7 and 7 times 9, 9 times 11. So basically like multiplying consecutive odd numbers. So if we follow this pattern back, we would need to do -1 times 1, which would give us -1. And you can see that that would be this point right here for the 0th term. And then if you follow this backwards again, you'd have -3 times -1, which equals +3, which would be this point right here for the -1th term. And then if you do negative 5 times negative 3, that gives you positive 15, which would be this point. And you kind of get this symmetrical pattern um, where the negative third term would be the same value as the third term because negative 5 times negative 7 would still be a positive 35. So, my dad's sequence is an example of a pattern that could be described by a quadratic function. And when you're writing quadratic functions, there's three different forms that they're typically written in. So, in the first form, standard form, basically you have no parentheses and you just have an x squared term, an x term, and a constant term. In factored form, it's written where the structure of the expression is that you have two terms that are multiplied. Well, actually, it'd be more accurate to say two factors that are multiplied because terms are added together or subtracted and factors are multiplied together. So that's why it's called factored form, is because you have factors that are multiplied together. And then the last form is called vertex form, and I'll tell you why it's called that in just a second. But vertex form is basically where you have like some factor that's squared, and then a lot of times you'll have a constant that's added to the end. So, the basic idea of how you convert between these forms is if you wanted to get from either vertex form or factored form back to standard form, you would just multiply out the factors. So, like you would FOIL x plus 5 times x minus 1, and that would give you the standard form. And same thing with vertex form. If you were to FOIL this out and multiply x plus 2 times itself and then subtract 9, both of those would end up giving you the standard form. To get from standard form to factored form, you do factoring, which in high school algebra, you do a lot of it, and I'm not expecting you to remember all of that. So I will give you all three forms on the homework or on the test. But the way that you get from standard form to factored form is by factoring. And the way you get from standard form to vertex form is by doing a process called completing the square. So if you want to look it up for your own curiosity, you're welcome to. But I don't expect you to do that for this class because this is one topic out of like three this week. And I don't expect you to remember everything from high school algebra to be able to do this one topic. So I will give you all three forms, but I do want you to know what each of these forms communicates about the quadratic function that it describes. So on the right-hand side here, we have a graph of the quadratic function that's represented in these three forms. And if you look at standard form, the constant in the standard form corresponds to the y-intercept of the graph. And the reason for that is because the y-intercept happens when x is 0. So like on the x-axis, if you go to 0, that's where the y-axis is. And if x equals 0, well, x squared is just 0, and 4 times x is also 0. So the constant at the end of the standard form represents where the y-intercept will be. And then similarly, if you look at factored form, the different factors tell you where the x-intercepts will be. Because the x-intercepts happen when y equals 0, or you could also say f of x equals 0. And that number will be 0 when either one of the factors equals 0. So the thing that makes this factor equal 0 is when x is negative 5. So that's why one of the x-intercepts is at negative 5. The thing that makes this equal 0 is a positive 1. And so that's why the other x-intercept is positive 1. And then for the vertex, you can use vertex form, which is why they call it vertex form. And that will tell you what this point is right here. So this point is the lowest point on the graph, or sometimes parabolas will be like upside down, in which case the vertex would be the highest point. But that point will always happen when the squared part of the vertex form equals 0. And so the thing that makes that squared part be 0 is when x is negative 2 So that's the x coordinate of the vertex. And then the y coordinate is just the constant that's at the end of vertex form. Because if this stuff equals 0, which it does when x is -2, because -2 plus 2 will be 0, 0 squared is 0, then the output, or f of x, or the y coordinate, is going to be 0 minus 9, which equals the -9. So standard form is good for finding the y-intercept. Factored form is good for finding the x-intercepts because there will usually be two of them. And then vertex form is helpful for finding the vertex of the quadratic. So those are just some features to know about quadratic functions and their graphs and the relationships between the different ways you can write the equations. And again, I'm not going to expect you to convert between these different forms. I will give you all three forms, but I do want you to know the relationships between the forms and the different features of the graph that those forms can give. So the last thing I want to mention about quadratic functions is a comparison between exponential and quadratic functions. So remember, an exponential function is found when you're repeatedly multiplying by something, and a quadratic function is when you multiply the input by itself. So I have two super simple exponential and quadratic functions here. So in this exponential one, you're repeatedly multiplying by 2. And in the quadratic function, you multiply the input by itself, and that's it. You don't add or subtract or multiply anything else. So these are two very simple examples. And if you look at both of them, you'll notice that as you get bigger and bigger inputs, they both curve upwards. So you can see they're both curving upwards. However, the difference is when you go in the negative direction, a quadratic function is still going to curve upwards because if you square a negative input, a negative times a negative equals a positive. But with exponential graphs, if you have like a negative exponent, that's the same thing as dividing by that number a certain number of times. And so you're going to get closer and closer to 0 as you go in the negative direction. And another thing that's different is if we look at these two graphs where we've zoomed out, a exponential function is going to grow way faster. Because if you look at this, the exponential function reaches an output of 300 around about an input of 4-ish, I think, about right here. Or actually, that's about 8, because each of those tick marks represents 2. But this one reaches an output of 300 around 8, versus the quadratic function. It took it until about maybe like 18 or 17, like an input of 18 or 17 in order to get to the 300. So the exponential function will grow much faster than a quadratic function will. So that's just a quick comparison between quadratic and exponential functions. But the main thing that I want you guys to know from this video is that quadratic functions involve multiplying the input by itself, and the various features of the quadratic function you can get from the different forms of quadratic equations. So if you have any questions, let me know, and I hope you have a good day.